So to begin my Chemistry 2 series, we're going to start off the series with intermolecular forces. So intermolecular forces are forces in between individual molecules. So different molecules, not the same molecule. So there is one water molecule. An intermolecular force will be a force between that molecule and another molecule. And for this example, I'm using another water molecule. So the intermolecular force, I'll say, will be in blue, will be a force such as this one, in between two separate molecules. An intramolecular force is a force that holds a molecule together, so it will be a force in between the oxygen and the hydrogen attached together. So once again, blue right here is an intermolecular force in between two molecules, two different molecules, and an intramolecular force is in between a force inside one molecule. Okay, so now we're going to elaborate on the different types of intermolecular force. So we're going to forget about intra for now. We're going to talk about intermolecular forces. So here I have the list of the different types of intermolecular forces we're going to go over. And the first one is going to be dipole-dipole forces. And what I have drawn right here is a good example. So So a dipole-dipole force is the force in between two different polar molecules. So here is a water molecule, which is polar. So polar meaning it has a dipole moment, meaning a partially positive side and a partially negative side. So the partially negative side is going to be on the oxygen, and the partially positive side, which we'll do in blue, will be a hydrogen. Okay, so as you know, opposites attract. So the partially positive side, or let's start off, the partially negative side will be attracted to the partially positive side of another water molecule. So on the other water molecule, remember this hydrogen is partially positive. And then that looks bad. Let me make that look nice. There you go, plus. That looks better. Okay, and then has its partially negative charge here. So once again, a dipole-dipole force is a intermolecular force between one polar molecule and the other polar molecule. The partially positive side of one polar molecule being attracted by the partially negative side of another polar molecule. So dipole-dipole you can think of between a polar and a polar intermolecular force. So pretty easy, right? Now, ion-dipole. So based on what I said before, dipole-dipole is polar-polar intermolecular force, and ion-dipole, we'll use water again, is an intermolecular force between an ion and a polar molecule. So once again, ion-dipole, between an ion and a polar molecule. So here's our polar molecule. So let's pick an ion. Let's say we had a Na plus, an ion. This is in a solution of water. So there it is next to another water molecule. And like we said, the water molecule is polar, so it has a partially negative side and a partially positive side. Okay, so because the ion, which is sodium, has a positive charge, is going to be attracted to the partially negative charge. So therefore making an intermolecular force. Right there. The ion, so for an ion-dipole force, the ion is attracted to a polar molecule. And because it's positive, it's going to be attracted towards the partially negative side. If we had another ion in there, say we had Cl minus, it has a negative charge, so it's going to be attracted to the partially positive side of the water molecule, in this case the hydrogen. So there's an example of ion-dipole force. Alright, so that's two down. Dipole-dipole forces, dipole-dipole in between a polar and a polar molecule, and the ion-dipole in between an ion and a molecule with a dipole, meaning another polar molecule. So two down, four more to go. Now for dipole-induced dipole. Now let's talk about this. Let's say we have methane, CH4, which is not a polar molecule. It does not have a dipole moment. It's nonpolar. But say it's in a solution with water, and we'll put water right here. Alright, so this may be a little hard to grasp, but I assure you it's pretty simple. Now, first of all, we have to indicate the water is polar, correct? So it has a partial negative side and a partial positive side. So once again we're talking about dipole-induced dipole. Now this methane is nonpolar. Let me write that on there so we're clear on that. Methane is nonpolar, meaning no overall dipole moment. But when it's next to this water molecule here, let's look at this particular bond right here between the carbon and the hydrogen. One bond, meaning there's two electrons right there that's being shared between the carbon and the hydrogen. And so the electrons are basically going back and forth in a circular motion, just like this. Now, here comes this water molecule coming close to this bond right here between this carbon and hydrogen. Now, this oxygen is pointing towards the bond. It has a partial negative charge. So, negative charge right here, and these electrons are also negative. So, they have the same charge, meaning they're going to be repelled. So these electrons, which were going back and forth before, once this oxygen comes closer, they're going to be repelled and be around the carbon a lot more, therefore creating a instantaneous dipole moment for that molecule. So if the electrons around this carbon a lot more, that's going to create a partial negative charge on the carbon and then a partial positive charge on the hydrogen, creating a dipole moment on this otherwise non-polar molecule. So, which creates basically an intermolecular force between this partial positive hydrogen, new partial positive hydrogen, and the partial negative oxygen. So that's why this is called a dipole-induced, because this dipole moment was induced by a dipole. Dipole-induced dipole. Pretty simple. Okay, so that's another intermolecular force out of the way. Now we have to talk about ion-induced dipole. Now if you think about it, the one we just did was when a polar molecule came next to a non-polar molecule, and due to the dipole moment of the polar molecule, it induced a dipole moment in the non-polar molecule. So a dipole-induced dipole. This dipole was induced by another dipole. So when we come to the next one, ion-induced dipole, so a dipole was induced, but this time it's going to be by an ion. So basically the same scenario, but I'll do it again, just so we're clear. So let's talk about this methane again, which is nonpolar. Don't have to write it because I wrote it right under this. Nonpolar, no dipole moment. But, okay, so this time we're going to do an ion. And, we'll do the sodium again. Na+. So once again, the methane right here, the CH4, is nonpolar, and in this particular bond between the carbon and hydrogen, there's electrons going back and forth, so back and forth. But when this ion, the sodium ion, comes over here in proximity of this bond, has a positive charge, the electrons are negative. So in this case, they're opposite charges, so the electrons are going to be pulled towards the hydrogen a lot more, creating a partial negative charge on the hydrogen, and then a partial, oh that was ugly, a partial positive charge on the carbon, inducing a dipole. So that's why it's called an ion-induced dipole in this case. And there's the intermolecular force between the negative charge partially negative charge hydrogen and the positive charge sodium. So in both cases, for this one, well, hold on, let me put a check there because we did ion-induced dipole. So in both cases, for this one up here, this top one is a dipole-induced dipole because this non-polar molecule had a dipole induced in it by another dipole. And in this case, a dipole was induced by an ion. So ion-induced dipole and then dipole-induced dipole. Now, as you can see, the dipoles are opposite, but that doesn't matter. All that matters is that a dipole was induced. Okay, so next on the list is dispersion forces. Now, dispersion forces may be a little tricky to understand, but I promise you it's pretty easy once you get the hang of it. So if we look at both of these molecules here, they're both nonpolar, meaning no dipole moment. But dispersion forces are found in all molecules, no matter what, even nonpolar. And the reason is, if we look at this bond right here between the carbon and hydrogen, once again, two electrons going back and forth. But just say for one moment in time, for one instant, one fraction of a second, both of the electrons are here. Just for a fraction of a second. So we just froze time. Both the electrons are over here. So that means there's going to be a partial negative charge here, just for an instant. Not overall, but just for one moment in time. And therefore, in one moment of time, it's going to be a partial positive charge here. Okay? So meaning, this is a instantaneous dipole moment right here. This is an instantaneous dipole moment. So this positive charge is therefore going to influence the electrons in this bond right here, which is going to attract the electrons. Whoa, didn't mean to do blue. I want to confuse. There. Alright, there we go. Attract the two electrons in this bond between the hydrogen and the carbon to right here, therefore creating a partial negative charge right here and a partial, there we go, positive charge here. So therefore inducing a dipole over there. Now these dispersion forces are found in all molecules, even nonpolar, because even though the reason why these molecules are nonpolar, even though I just showed they do have a dipole moment, is that this dipole moment only lasts for an instant in time. And in fact, it can reverse. These electrons will be pulled over here, and the dipole will be reversed. And so, overall, average through time, the overall dipole moment will be a net zero. It will be canceled out. But just for a moment, these two will be attracted to each other. And then for a different moment, they could be repelled. So it goes back and forth. So that is the explanation for dispersion force, which can be found in all molecules. Alright, so I ran out of time to go over hydrogen bonds, but just to recap, dipole-dipole forces are between a molecule with a dipole and another molecule with a dipole, so one polar molecule and one polar molecule. An ion dipole is between an ion and another molecule with a dipole moment, so between an ion and a polar molecule. Dipole-induced is between a non-polar molecule and a dipole molecule, meaning a polar molecule. And then ion-induced dipole is between a nonpolar and an ion. And dispersion is found between all molecules because of the instantaneous dipole that can be formed between the electrons going back and forth.